Okay, inequalities part one. So before we get started on inequalities, we're just going to talk about different notation. So what you've been using all along is something called set notation for when you state your domain and range. But we're going to learn about interval notation, and I find actually interval notation so much easier than set notation. And it's how we write our solutions, and it can be a lot smaller, as you can see, the difference between the two. Those are both meaning the same thing. And so some little notes before we get started. I'm just going to get the page that you have in your books. So when we have an open circle, that is always means it doesn't include it, right? It's not equal to at that point. And so that's going to be an open or round bracket. Okay, and if it's equal to at that point, or filled in, that's something called closed, a closed circle. So it's going to be closed or a square bracket. So an open bracket looks something like that. It's rounded, and closed would be the square bracket. So for each of these, we're just going to write on the left here our interval notation, and we already have set notation given to us. So here this means x is greater than a but less than b. So what we would say if it's between a and b, it's not equal to a, so a would be a round bracket, comma, to b, which is also a round bracket because it's not equal to. And so those mean the same thing. They're just different notations for domain and range. So the next guy, because of the equal to symbol, the difference would be that we'd use square brackets. It's equal to a, or it's greater than or equal to a, and less than or equal to b, so we'd use square. So in an event that it's between a and b but not including b, you'd square bracket for a, comma, b round bracket, or vice versa. Round bracket for a, so if it's not equal to a, but it's greater than a but less than or equal to b, we use square bracket for b. So very simple. So what do we do in the event of infinity? So we used to write an inequality when x is greater than a. That would be our set notation. But now we want to always say it's between two things. Well, technically, it's between a and positive infinity. But positive infinity is not a set number. So we would actually use a closed bracket. We always use a round bracket for infinity. So we'd write this as a, comma, to infinity, bracket. So you get to have fun writing the infinity symbol now. So, and the next guy, it's equal to a, so a is a square bracket, comma, to infinity. And again, infinity, we always use, positive infinity, we always use a round bracket. So same idea. If we're from, in this case, what are we between if we're less than b? Well, we're between negative infinity and b. And so we'd write that round bracket, negative infinity to comma b, and it's not equal to b, so round bracket. And same idea here, except for now we're equal to b, so negative infinity to b closed. And then if it's all real numbers, well, what is it between? It's between negative infinity and positive infinity. Okay, so that's, we actually always write it in between two values, and we have to use the symbol of infinity. So that's set, yeah, so that's our notation there. So that's interval notation as opposed to set notation, which is what you're used to. Okay, so unions and intersections. So often in calculus, we need to compare two or more different sets of solutions. So we use union and intersection. So union is basically the union of two solutions, bringing them together. So union is an or situation. It's this or that. It includes both. Where intersection is just, okay, where's the overlap, right? The overlap of our two solutions. So let's consider these two sets. So we have, and we're going to answer, so let's consider these two sets. So we have set R, which is from negative 3 to infinity. We have set S, from negative infinity to 1. And then set T from 5 to infinity. So let's look at the union of R and S. Okay, so the union of R and S, if we do a number line, And we're going to put on r has -3, and it's greater than and including -3. So that's r. It's greater than -3. And s starts at 1, and it's less than 1. Including 1 and less than 1. So if we're doing the union, we want to include all solutions. So the union, in this case, would be all real numbers, or another way to write that, because we want the both are available answers, the union includes all values, would be -infinity to infinity would be our solution. Okay. So let's look at the same idea, but now intersection. So if we look at the same idea, r and s, so how I always remember it looks like an and for and is intersection, versus union looks like a U. So intersection, again we had r and s, so r was greater than or equal to 3, and s was less than or equal to 1. So now we want the overlap, and where's our overlap? Our overlap is between -3 and 1, including -3 and 1. So our solution here would be the intersection of r and s is -3 to +1. Maybe I won't box it. Okay? We're using closed brackets because it is equal to at those points. Let's try another 2, s and t. Okay, so s, we have 1 and less than 1, and t is greater than or equal to 5. Okay, so the union, well, how do we actually state, we have two different areas here when we want to be all inclusive in a union. So we want both our available solutions. So we're going to write them separately, because here for, I believe it was s, it was -infinity to +1. And then we're actually going to write the union symbol. So or 5 to infinity. Okay, so that would be our solution, because it's this or that in a union. Now in an intersection of the same case, well, if we look at that again, was there ever an intersection point? And the answer is no, they never intersected. They were totally two different areas, and there was no intersection. So what would you say for that? Well, it's an empty set, okay? So you would either write this symbol, so not definable, or just the empty set, so a set with nothing in it, because there's no solution. Okay, and our last one, r and t. So on our number line, r, I believe, yeah, greater than -3, and t is greater than 5. Okay, so if we're looking at the union of this one, the union would then just be greater than -3. From -3 to infinity would be the union of those two solutions. Okay, whereas if we looked at the intersection of the same case, well, where do they overlap? Well, they only overlap greater than 5, when x is greater than or equal to 5, and so the intersection would be from 5 to infinity, be the intersection. Okay, so we're going to use union and intersection in the part 2 of this lesson, when we're dealing with inequalities that have quadratics in them and absolute values. Sorry, yeah. So let's move on. Okay, linear inequalities. Remember, linear is anything with degree 1. So move all variables to one side of the inequality, move all numbers to the other side, and then isolate the variable, express the answer in interval notation. Remember, if you multiply or divide by a negative, then you have to actually flip your inequality. So that's a review from last time. So here's an example of a linear, because it's degree 1. So we're going to get all the x's on one side and all the constants on the other. So it doesn't matter how we move it. I'm going to bring the x's to the left, so subtract 8x to both sides. Minus 6x minus 11 is less than 13, and then add 11 to the other side. So we have negative 6 is less than 24, negative 6x. And when we divide both sides by a negative, remember we have to flip. We multiply or divide by negative. We flip the inequality. So x is greater than negative 4. Okay, but how would we write that now? Instead of writing our inequalities in set notation, we're going to actually write interval. So that's when if it's greater than negative 4, our solution is, it's not including negative 4, so it's a round bracket to infinity. Negative 4 to infinity would be our answer. Okay, so what if we have a quadratic? Okay, so inequalities of simple squared variables. So if it's very simple, like this, it's not a complex quadratic, we don't have to go ahead and make a chart. We could just basically reason our way to the solution. So if you look at x squared is greater than or equal to negative 8. Let's go through an example first. X squared is, when is x squared greater than or equal to negative 4? So think about it. What numbers when squared will be greater than or equal to negative 4? And really, any real number will work here. Why? Because when you square any number, it's going to give you a positive. Since squaring creates a positive number, and all positives are greater than negatives. So in this case, it's all real numbers, or it's our solution. So negative infinity to infinity, or you also know that as XER, okay? All real numbers, so that'll be all the case. So no matter when we square a number, it's always going to be greater than a negative. So let's look at the other side. What if we have x squared is less than or equal to negative 8? So when we think about this, let's look at an example. What number, when squared, will be less than or equal to negative 4? And so using the same reasoning as last time, no matter what number you put in there, it won't work, because no values, when squared, will be less than negative 4, less than or equal to. Because you're always going to have a positive, right? A positive, it'll be no positive is less than a negative. So here we have empty set. So this undefined. Okay. There's no solution, right? There is no solution, so it's not possible. So whenever we have a negative, x squared less than or greater than a negative, it's either going to be all real numbers. Well, in this case, less than would be no solution. If it was greater than a negative, be all real numbers. So let's try and reason through this example. So if we had x squared greater than 4. So if we think about it, what are the critical values here? Okay. So what numbers when squared will be greater than or equal to? So let's start with what would equal to 4. What values of x will equal to 4? And those are what we call critical values, or endpoints. Okay? So the critical values here, well, if we square root both sides, or what numbers, when you square them, equal 4? The critical values in this case are positive and negative 2. Okay? So So we have to figure out, okay, so is it going to be between -2 and 2, or is it going to be less than 2 and greater than 2? So we have to figure that out. So when you think about it, here, let's try putting in 0. If I square 0, will that be greater than 4? And the answer is no. So it has to be numbers less than or equal to -2 or greater than 2. So try number. -3 squared is 9, which is greater than 4. Or +3 squared is also going to be 9, which is greater than or equal to 4. So our solution here is between -infinity and -2, or, so the union, between 2 and infinity. Okay, so if we compare that, so as when is x squared greater than or equal to +a, well, it would be, if we write this as an inequality, when x is less than or equal to -√a, or when x is greater than positive √a. There's a plus or minus, because those are our critical values. Our critical values would be plus or minus √a. Okay, I'm going to show you another way to solve these later, but one way, if it's just a simple quadratic inequality greater than a constant, is to reason your way through it. Okay, figure out the critical values and then test it. Test each component and see where it fits. Okay, so let's look at the next one. So same idea. What are our critical values? Well, square root both sides, plus or minus 2, right? Plus or minus 2 is when x would equal to 4. That's how we get, when would that be equal to each other? So our critical values are plus or minus 2 again. So we want, this time, when we square a number, is it going to be less than 4? And so let's test an area. Would it work in here at -3? So -3 squared is +9. Is that less than 4? No. How about 0? 0 squared is less than 4, yes. So it's going to be the area in between here. And then test greater than 2. 3 squared is not less than 4. So our solution is between -2 and 2. And so same idea. So our solution would be between -a and a. And if we write it as an inequality, so when x is greater than -√a and less than or equal to +√a. Okay. So we're really using that idea that we're going to test each interval, figure out our critical values, test the interval, and see what works. So let's look at other quadratics. So if you're dealing with a quadratic, so yours, you have to fill in a couple things. You put everything to one side of the inequality. So we want everything to one side whenever we have a quadratic that doesn't deal with just like x squared greater than or less than a constant. And we're just going to put everything to one side. So make one side equal to 0. Then we're going to factor, and the factoring is going to give us our critical values, our endpoints. Okay? And so this symbol here should be different. There you go. So there's two places we have critical values, when our numerator is 0 or when our denominator equals 0. And if our denominator equals 0, right, that means it's undefined, right? You can't divide by 0. So all critical values will come from those two locations. What would make my numerator 0? What would make my denominator 0? So do an interval test, and you've done those in grade 11, so we'll review that. And then test each region defined by the critical values, state our answer. So let's look at an example, because there's a lot written there. So again, here I have x squared is less than or equals to 7x. So we want to bring everything to one side of the inequality. So I'm going to subtract 7x to both sides. Now that we have one side is 0, we're going to factor. So factoring out x, we can now see our two critical values. What would make this function equal to 0? Well, there's two values. Our critical values are when x is equal to 0 and 7, right? They're basically what would the x-intercepts be. Those are our critical values. So when we do an interval test, I'm going to show you the chart that you've done before, and then also with the number line. Okay? So what you've done in the past, you have basically, if you put this on a number line, and be very careful because this doesn't have an equal to symbol underneath. So these are open circles. So 0 and then 7. Okay, well, there's 3 different intervals we have to look at. Okay, we're going to have to test from negative infinity to 0. We're going to have to test from 0 to 7. And then from 7 to infinity. So these are my 3 intervals. So if you have 2 critical values, you'll have 3 intervals. Always one more than the number of critical values. So those are my intervals. Now what we want to do is test whether it's going to be positive or negative, and then what would the product be, the actual function. So we'll do x, and then the other factor is x minus 7. And so what would that make the product, positive or negative? So we're going to do a test, each one. Done these before back in the day. Probably didn't love them too much. Okay. And so using the chart, which can be a lot of writing, we're going to test, okay, x. So between negative and 0, negative infinity and 0, x will always be a negative. This will be a negative value. Between, and then x minus 7, so pick a value. So really what you're doing is you're picking a value between negative infinity and 0. So say negative 1. And plug it into x minus 7. Negative 1 minus 7 would be a negative, always. Okay, so any number you plug in from negative infinity to 0 in here, when you plug it into x minus 7, any number, choose a number, so negative 2 minus 7, just figure out if it's positive or negative. Okay, so what does that mean for our function at that point? Well, it means that if I have a negative times a negative, our function will be positive between negative infinity and 0. Okay, so then between 0 and 7. So pick a number between 0 and 7. So I'm going to use 1. Okay, so if we plug in 1 for x, that's a positive. 1 minus 7 would be a negative. Any of the numbers between 0 and 7 would be negative. So the product of the two is going to be a negative value. So between 0 and 7, it'll always be negative. And then we do the interval from 7 to infinity. So 7 to infinity, choose a number, say 9. So 9 is positive, it's just x. 9 minus 7 would give you a positive. And so the product of the two would also be positive. Now the question is asking, so we're looking here. We want, when is our function, x times x minus 7, less than or equal to 0? Less than, it means negative. When is it negative? And so it's negative right here, between 0 and 7. So our solution is between 0 and 7. When x is greater than 0, less than 7. That's our answer. Okay. Now, you could have done these. I usually don't make the full chart because I find it's a lot of work. So how do we do the same thing with less writing? Well, I use a number line as well. So what I would have done, I'll do the next example without the chart, but still doing the same process, just less writing. So let's look at another example. Example 2. X squared is greater than x plus 6. So we need everything to one side. I always like to keep x squared positive, the leading coefficient positive, because then factoring is a lot easier. So we have subtracting the x and the 6 over. We want to solve, when is x squared minus x minus 6 greater than 0? So now we factor. So get one side greater than, I have 0. One side of the equation should be 0. And now we're going to actually factor. Sorry, inequality. Okay, so sum product. We want a sum of negative 1 and a product of negative 6. So that would be negative 3 and positive 2. And you can go straight to factor 4 when it's a simple trinomial, or you still, if you want to break up the middle term and use grouping, you can. But we can actually just go straight to factor 4. So x minus 3 and x plus 2 is greater than 0. So what does that do for us? Well, it gives us our critical values. So where would the graph change from positive to negative? And that's always at our zeros, right? If you think of our function, our x-intercepts, if you had some function, so this one's opening up, and it has a y-intercept of -6. So very roughly sketching this function, x-intercepts are 3 and -2. Okay, so this function here, we're not using our graphing calculators. We want to be able to solve these without graphing calculators. And you did it in the past with a graphing calculator. When is this function greater than 0, above 0? So I reasoned my way to the solution by knowing the x-intercepts and whether it's opening up and down. But how do we do it with like interval notation? Because you need to practice that for more complex problems and more complex functions. Well, the critical values, you can see on your graph, where does the graph move from up above the x-axis or below is always the x-intercepts. That's where it's going to change from a positive to a negative, or vice versa. So we state our critical values at x equals 3 and -2. Okay, and we're going to put them on a number line. So our number line, we have -2 and 3. So these are the points where the graph will change from a positive to a negative. So now I would need to pick a number and test it. So for example, in this interval here, I'm going to choose -3. So any number between negative infinity and -2, so say -3. Then I plug it into this function here. So -3 times -3, so I plug it into each factor and figure out if that's a positive or a negative. So -3 minus 3 would be a negative, times -3 plus 2 was also a negative. And so this function here, 2 negatives, gives me a positive. So then I pick a number between -2 and 3. So let's test this interval. I'm going to use 0 because I find that's the easiest. And again, we'll do one factor at a time, whether it's positive or negative. So first, 0 minus 3 will always be a negative. And then 0 plus 2 will always be a positive. And so a negative times a positive, it's going to be a negative in that part of the function. And then between 3 and infinity, so in this area here, pick a number. I'll choose 4. 4 minus 3 is a positive. And then 4 plus 2 is a positive. And a positive times a positive will be a positive. And now we can go back to this. Okay, we want, when was it greater than 0? Our function greater than 0. So we were greater than 0, or positive, between -infinity and -2. If I just highlight, where's my highlighter? So we were positive from here and here. Right? And including 2, and including 3. Nope, not including open circles, because it was an equal to symbol there. So that's, we want open brackets, -infinity to -2, and then or union 3 to infinity. And our final solutions will have unions in them. You'll never have an actual final answer with an intersection, because you can always write an intersection more simplified. Okay, there it is. Let's look at another example. Example 3. So what students do here is they make a mistake of wanting to times both sides by x minus 5. And you can't do that. The reason why you can't do that is if you did that, you're going to actually take away a critical value, right? A non-permissible value, x equals 5. So whenever we have a rational expression, whether it has a quadratic in it or not, we just want everything to one side. We want one side to 0. So don't try and get rid of the fraction, because then you're going to be eliminating critical values, or points that are non-permissible values, which are very important in our solution. So in this problem, our first step is to actually subtract 3x to the other side. So we want everything to one side to 0. Okay? And usually that's, other than a linear, if you have a linear inequality, always get one side equal to 0. That's kind of rule of thumb, unless it's linear. So it's just very quick inequality, easy inequality. Everything's degree 1. It's not a rational expression. That's the only case where you actually can move x and solve. But every other case, we want one side equal to 0. Okay? So how are we going to be able to combine these to subtract them? We need a common denominator. So 2x squared plus x, and then I have to multiply top and bottom of 3x by x minus 5, so that we can get a common denominator. Let's simplify this. 2x squared plus x, and we'll bring in the negative 3x, minus 3x squared plus 15x. And see if we're going to need to factor here, but collect like terms. Negative x squared and plus 16x over x minus 5. Okay, so let's factor. I like to have x squared positive, or the x positive. Let's pull out the negative there. We can factor the numerator, so let's do that. So I'm going to factor out the negatives, negative x. And we're going to be left with x minus 16. And all over x minus 5. Okay, so we have some critical values here, and we want to state them. So our critical values are when our numerator is equal to 0, so when our function is equal to 0, or when our function is undefined. So really what that means is, okay, when our numerator is 0, when is our denominator 0? So our numerator is 0 when x is, because now it's factored, you can see when x is 0 or 16. And when is our denominator 0? When x is 5. So we actually have 3 critical values, meaning we have 4 intervals. Okay? So drawing the number line, put all our critical values in here. Now I like to actually, the non-permissible value, it can't equal to at that point, right? So when we place that one, so 0, let's do 0 and 16, so 0, which is, it's going to be filled in, 16, because of the inequality, but at 5, that's actually, I like to actually draw in my, right, that's going to be an asymptote, because that's what, when our denominator is 0, always produces an asymptote. That will always be an open circle. Okay? So that's a non-permissible value. Because that's going to, a common mistake is to actually, because students will see the equal to symbol in the equality, they'll actually fill in 5, but really that is a critical value that occurred because of the non-permissible value. So that's always an open circle. Okay, so we could do a chart. I'm just going to use my line. Now what you have to be very careful is this negative in the front of the function. So we have to include that in our test. So we're always going to have the negative in front. Okay, so the negative in front, and then we plug in our values. So I pick a number between negative infinity and 0, so say negative 1, and we're going to plug it into each factored form. So we first, if I plug in negative 1 to x, that gives me a negative. So we have the negative in front, and that would be a negative. A negative 1 minus 16 would be a negative. And then divided by negative 1 minus 5 would be a negative. Okay, now you could do a chart if you wanted to, and I could show you how. I have a tendency to just do my test like that, and then it gives me my answer. So 4 negatives results in a positive. Okay, so now I'll pick a number between 0 and 5, so I'll choose 1. So we have the negative out front, and then plugging into x, 1, positive 1 is positive, 1 minus 16 is negative, and then 1 minus 5 is negative. So we have 3 negatives and a positive, gives us a negative. Okay, pick a number between 5 and 16, so say 6. Do the negative out front, and then plugging in positive 6 for x is a positive. 6 minus 16 is negative, and 6 minus 5 is a positive. So we have two negatives, two positives. That will result in a positive. And then pick a number greater than 16, so say 17. We have the negative in front. And negative, so 17, positive 17 for x is a positive. 17 minus 16 is a positive. And 17 minus 5 is a positive. So three positives and a negative give a negative. So we want, and our solution is when our function is less than or equal to 0. So we want a negative. So our solution is here and here, between 0 and 5 and greater than 16. So when you write this, be very careful. So 0 is closed because it includes 0. 0 to 5, but 5 is open because it's a non-permissible value, it's an asymptote. Union 16 is square bracket to infinity. Okay. Now, if you actually did a chart for this, if you wanted to do the chart, just on a side note, so we would be working with this function right here, right? So I still would list my critical values. So we have our intervals. We have three critical values. So we have four intervals: negative infinity to 0, 0 to 5, 5 to 16, and then 16 to infinity. Okay, so those would be my intervals, and then I would put in, I could just go negative each factor. X minus 16, x minus 5, and then our function, so the product of all of those. So could have done the same thing to get our solution, and then you would have still subbed it in. So between negative infinity and 0, say negative 1. Negative 1 would be a positive. From 0 to 5, if I plug in 1, negative 1 is negative. 5 to 16, plug in 7. Negative 7 is negative. And then 16 to infinity, plug in 17. So negative 17 is positive. And then go through that again, right? So pick a number between negative infinity and 0. Negative 1 minus 16 is negative. I'll go across the whole row. Negative 1 minus 5 is a negative. And so here we go. You have two negatives and a positive is a positive there, which is what we got. You can see. And then pick a number between 0 and 5, positive 1. 1 minus 16 is a negative. 1 minus 5 is a negative. 3 negatives is a negative, which is what we had. Pick a number between 5 and 16, so 6. 6 minus 16 is negative. 6 minus 5 is positive. Two negatives and a positive give a positive. And then last, pick a number between 16 and infinity, so 17. 17 minus 16 is positive. 17 minus 5 is a positive. Three positives is a positive. Ooh. What did I do wrong? This guy was a negative here because we had 17, negative 17. So there we go, a negative. So that would work still, and we want when it's a negative value. So our solutions were the union of 0 to 5, 16 to infinity. And then just be careful of the open closed. So a chart would work. It's up to you which method you use. As the course goes on, I just find the chart so much work to write when I could just do the test right above the number line. So yeah, that's part 1 of lesson 5.